So today I'm going to talk about, as you can see on the screen, input to state safety and some variations of control barrier functions theory to basically get a sufficient condition for input to state safety and how we can use these to design robust safety critical systems. This is all right. So this is a work that I did mostly in University of Michigan with my advisor Professor Gabor Oros. And I also got a lot of support from Professor Aaron Ames, and as well as his students. Now is working at Motional, Andrew Taylor. And some of the experiments that I'm going to show you some videos, those experiments are made by the valuable introduction of Chao He. Now he's a professor at University at Buffalo. So if I want to start with the motivation, with the modern engineering systems becoming more and more complex, it is penetrating through everyday life. There's a certain requirement where the safety critical systems, we want to have some formal guarantees when we are designing for their controllers. These systems may be fully autonomous systems, semi-autonomous systems. They may cooperate with themselves. For example, in an industrial plant, you can educate your workers to cooperate with these autonomous machines such that machine can expect human operator to behave some certain way. Or it can be just a traffic network where you cannot expect a cooperation. But in all of these cases, you want your autonomous system to safely operate in the presence of especially other human. So the way that I see it, to really achieve the safe autonomy, I think there's a certain road. And I believe this is correct for most of the safety critical controls. To start with, I think everything starts at the theoretical foundations, and hopefully studying theory well will give us some design framework, and implementing these design frameworks for particular problems and some computational issues being solved, we can get some data. And at the end of the data, I believe we will see some gap between what we expect from our theoretical assumptions and what we actually get in practice. But I believe this is not a weakness, but it actually gives us an opportunity to improve our design so we can always go back to the theoretical foundations. So I believe this road is not actually a direct circle to the safe autonomy, but it's rather a spiral with multiple iterations. So my talk will also kind of reflect a similar structure. For example, in the contents, I'll briefly talk about the theory, what I mean by the theoretical contribution. This is going to be a formal safety and how we can verify this using the control barrier functions. And in the implementation side, I'll briefly talk about the safety filter controllers, and it's going to be implemented to autonomous trucks. Autonomous trucks are going to give us a really good platform to show some of these characteristics that we may see in any of the other autonomous systems. And in the analysis part that I'm going to spend a little bit more time, because I think this is going to be more closely aligned with the audience probably here, where I'm going to introduce input to state safety. And I'm going to show that there's actually two types of input to state safety by the way that they are defined. And by investigating them in detail, I'm going to come back to the theory by finding some sufficient conditions and implementing these sufficient conditions back into the controller, which is going to give us some robust filters. And then at the end, I'm going to talk briefly about the outlook, what is being done in the literature and what we can expect in the coming years. So let's start with the theoretical foundation. When I mean So we're going to talk about safety. So let's first settle down what we mean by that. So we have this a nonlinear system. We work with the continuous time systems. We have this set of initial conditions and also an unsafe set that we don't want to go really. This is kind of like a sanity check that we have to make sure that the initial condition and the unsafe condition obviously cannot share some certain space. I'm going to name the solution of this system, the closed loop system, with x of t, starting from given initial condition. So the most basic safety definition is going to be any point in the initial set. If throughout the whole realization of the trajectory, if you do not visit any of the unsafe states, then this is considered as safe. But recently, there is more function-based safety definition is becoming more and more popular because we realize that if we can find a function that defines a certain set, we have to be careful. This certain set has to be a subset of the initial set. In that case, we can actually use a function-based definition. This is actually exactly similar or same to the previous one. But what is good is we can use this function in a constructive way to design controllers that actually lead us to this safety guarantee. So this is why I'm going to talk about when I say safety, I'll use the second definition. What we mean by safety eventually is throughout the realization of the trajectory, the evaluation of the function would not go beyond 0. The safety verification is a very well-studied topic in control. There are a lot of ways people try to crack this problem. Typically, or rather, in my research, I did lean on more set-theoretic methods. And what I mean by set-theoretic methods are when we study the properties of a system without really having to calculate any of those trajectories, if we can get an idea whether the safety can be guaranteed or not by just checking some certain property of the model, then we are in the set-theoretic field, basically. This field, I can say that is kicked this seminal work of Nagumo. You might have heard it before in the context of safety critical control. It's very popular. Basically formulates a very intuitive understanding, honestly. What it says is on the boundary, if we can calculating these tangent cones, if the system model is in the tangent cone for all the boundary points, that means that the system trajectories cannot leave the boundary. So it has to go either inward or be along the boundary. So this naturally leads to the safety. So this is a verification method. And throughout time, as you can see, there are other modifications to this theory. With the viability theory in the 90s and in early 2000s, we have the barrier certificates that is very popular with the hybrid type of cyber physical systems. But eventually, this leads us to all the developments in the 2010s with the control barrier function. It kind of is consolidated with this brand name now. So I will talk about control barrier function a little bit. The key idea is actually inspired from the Lyapunov functions, where we have this positive definite function. And if we can find a certain condition on the time derivative of this function with respect to the system trajectories, in particular, if we can actually upper bound this, then we actually will know that exponentially the system trajectories is going to approach to the equilibrium. So this is the main idea. What we can do is we can borrow this idea for the barrier function as well with a slight modification. So instead of this kind of positive definite function, you can think of this like a flipping the function and moving a little bit so that you basically create a set. The key thing here is we can still use this function h such that if in this time, if we can lower bound the time derivative of this function along the system trajectories again, now what we can say is we allow the system trajectories to approach to the set boundary s, but in a maximum rate, and that maximum rate is diminishing. So that means that at the very boundary, the system trajectory can either stay on the boundary or has to go in. So this is kind of the smart way of enforcing such a condition using the gradients. This is kind of the theoretical structure that we rely on when we talk about the control barrier functions. It basically allows us to construct all these nice properties and use this theorem. We start with the definition of control barrier function. It is basically if this function is a smooth function, it may be a big if, I do understand that. And if we can find this class K function, which is basically a linear function, can work. If for every point in this set, if we can find a control that can be lower bounded by this function, that means that this function is a control barrier function. And this certifies that this problem of safety is actually solvable. And indeed, we can solve this problem by using the function and the model as well. So this F is the model. Now I haven't realized I haven't introduced G, but G is, I'm considering a control affine system here. So it is x dot equals fx plus gx times u. So it gives us a very clear condition to lower bounds. One of the main criticism against control barrier functions, I guess similar to Lyapunov functions, is by itself, it is not a constructive method. And it is a right criticism because it assumes that there is a function that is controlled by a function. It doesn't really tell us how to find this. But there are some process or progress towards that direction as well. So there are some ways to construct functions based on your model or your input constraint, especially if it's tight. This becomes a very big problem. There are ways that you can calculate this function h by basically pushing it a little bit inward the set. You can do it online or offline. There are a lot of methods that is here. I'm not going to talk in detail about it. The focus of this talk is going to be more on the robustness side. So from this point on, I'm just going to assume that there is a function. And again, I understand it's a big assumption, but I still think that there's value, even though you assume that there's a function, you can still want to study its robustness properties. Now, with these theoretical foundations, it actually gives us the control barrier function gives us a design framework. And when it comes to implementing it, the most popular controller, I would probably say, is called safety filter. It is a very modular solution for safety critical controller. It is very much preferred because it takes this nominal controller, and anything can be nominal controller. Honestly, can be another optimal controller where you're not really considering the safety constraints. It can be a reinforcement learning. You're going to see a lot of papers about this, trying to make the reinforcement learning based controllers safe. It can even be a human operator, honestly. It's like, so you can actually put the human inside the loop as well. This is why this type of filters, the controllers, are very popular in the literature. Basically, the idea here is you're just penalizing the deviation from that nominal controller, because at the end of the day, this is the controller that you are trying to implement to your system. But you want to make sure that the result of this optimization problem always satisfies the safety condition that is given by the control barrier function definition. This optimization-based controller is pretty easy to implement because under mild conditions based on this set U, most of the time it is a quadratic programming, and there are really effective ways of solving this type of problem online. And what is more is actually we can ensure that the resulting controller is actually Lipschitz with respect to X, which is kind of a requirement. But what is even better is it's not very practical, or actually it is a very practical assumption, but if you assume that you have kind of a large input bound and practically you don't really have any other inputs, then this optimization-based problem actually has a closed form solution. You don't have to solve an optimization problem. And this closed form solution for a single case, it is given here. I wanted to give it here to give you an idea, because intuitively it actually tells us something nice. It means that the safety filter wants you to operate on the nominal controller as long as it is larger than this whatever the safe controller that you calculated based on the Lie derivatives. So it is pretty intuitive by itself. Here I'm basically going over the implementation of this idea for a particular example. This is a safe car following, where I'm designing a controller for the truck, and the truck is supposed to follow the leader in a safe distance. Now, distance is d, my speed is v, the leader's speed is v1, and it has an acceleration a1. And we know that there are some certain limitations, right? I cannot really use a huge braking, and similarly, the other car cannot really use a huge braking. So there are some limitations, and I need to somehow consider these limitations in my control barrier function design. The cruise control type of controllers typically rely on this time headway based unsafe set, where we are not only trying to keep a constant distance from the other car, but we are also trying to, so that distance also changes with my speed as well. This is a very, very common, I would say, type of safety assessment method in the autonomous vehicle design. And if we take this set as the set S, what we can do here is we can incorporate these limitations by basically pushing this set a little bit higher. And this will give us an S prime set, and exactly how much you need to push this at every point, it is a good question. Again, this is kind of how you can construct these barrier functions that kind of falls into that question. But in my work, I basically used a quadratic type of function where I can find these parameters such that whenever I start from this other set, if I basically implement my full break, I should be able to still be inside the set S. This problem, it is pretty easy. You can calculate these type of parameters using basically analytical solutions because it's a linear model and it's a linear set. So it's not a big deal, but by no means it is a generalizable approach. So for that, you have some numerical approaches. You can use Hamilton-Jacobi or another extension of control barrier function called backup control barrier function. So what we did is we implemented this controller onto truck. It was a very easy implementation. And we actually took the truck to the public roads. And you're going to see some videos on for this one on highway, where we are on the truck that is running autonomously and running this algorithm basically. So it decides the pedals, gas pedal and the brake pedal is basically decided by the outcome of the safety filter. And none of the other cars are controlled by us. So this is a uncontrolled traffic, basically. You have the radar cone you can see, and the headway plots with the purple, you see the distance sensed by the radar. And when you see this cutting, our safety filter was able to react safely so that you kind of make a slight break. It's not too much. You can adjust it by using some nice parameters. But everything works out really good on this like mild driving conditions. But obviously this is not enough for us. So we want to push this controller as much as possible. So what we did is we took the truck into a more controlled environment. And we want to see if the other car actually makes the full brake, an emergency brake, how would the truck react? As you can see, we still have some distance, so there's no physical collision, but that's not enough for us as a control designers who are after formal guarantees. Because what is important for us is here. As you can see with the way that we define safety, we wanted this function to be always positive. However, even with the filter, although I expect this to be positive, well, it goes negative. So there's a problem here. What is that problem? The problem is coming from the uncertainties. No matter how detailed you model your system, you will have to have some certain uncertainties, especially for this theoretical model. I just used the linear model. That means that my power train and the brake is ideal. So if I command a brake, I get that brake right away. But what is actually running underneath the truck is very complex and very complicated. Now, you can obviously try to design every module on the right-hand side, but it's not very scalable. It is not very generalizable, unfortunately. So rather than doing that, what we try to do is, well, can we just consider whatever this imperfection coming from the uncertainty as a disturbance to our control, and can we do something about it? So this approach basically brings us to this last and I think most important piece of designing a safety critical control, which is trying to bridge the theory with the practice. I believe this is a nice way to take a break, because so far what I did was I just talked about control barrier functions and safety critical controls. So for anyone who is not really have not heard these type of controllers, may have some questions. If you have any question, you can ask me. I think, as I said, this will be a nice place, because from this point on, I'm gonna start talking about the input to state safety and how we can get that property using control barrier functions. But if there's anything not clear up to this point, please let me know. And by the way, I cannot see if you're sending in a message. I cannot see messages. So if there's any message,
well, right now there are, I think, no messages which are new. Therefore, well, I have several questions, but I think they can be postponed till the end of your talk. So,
all right.
If nobody has other questions right now, then let's just continue.
Great. Okay. If there's any question, you can also let me know whenever. Again, as I don't see the chat right now.
Okay, great.
All right, thanks. All right. As I said, this is kind of a nutshell information about how to design safety critical control, or in particular, safety filter with using control barrier functions. But now we have a kind of a more challenging problem at our hand. Ideally, everything should work, but obviously in practice, we always have some certain uncertainties. But basically what we mean by uncertainties is we are using this type of gradients-based approach in control barrier function, where we always want this system dynamics to point inward to set so that on the boundary, we don't have any safety issue. But with the uncertainty, what we have is actually rather than just one vector, we have an array of vectors. So we want to make sure that all of them should fit inside the set. There are different approaches to this problem. I would say the first one would be if the nature of the uncertainty is distributed and it has a stochastic nature, then we have chains constraint control barrier functions where the outcome would not be 100% safety, but it would be 100% minus epsilon type of uncertainty. There are some constructive ways of doing that in the literature. If you're into that, I would suggest checking this paper, or you can just type in chance constraint CBF and you will see something. But I will not talk about that. I will more focus on the deterministic type of uncertainty, in particular when the uncertainty takes values from deterministic sets or with the bounds deterministic. In this case, you can say that there are two different methods. The first one is widely known as the robust control barrier function, where the main idea is to cancel the worst case at all circumstances. It makes sense. It's very intuitive. So you're trying to find the control that is going to eliminate the worst way the disturbance can affect your system. And if you have an idea, then you can basically do that. But it may be hard for some system. For example, if you have a very complex model and a very complex function, it can be hard to calculate this. Otherwise, maybe you don't have enough control authority to do that. So in order to, or for problems like that, we also developed another branch, which is the input to state safety. As you will see, this is coming from the input to state stability, actually. The idea here is, okay, what if we cannot really ensure this control barrier function condition, but rather we can get a graceful relaxation, which depends on how large the disturbance is. In that case, can we get some other formal guarantees how much the set or how much the violation can be? So in order to be more formal, this is what I actually mean now. I have the disturb control system, and I'm just taking the input disturbance for this case. It somehow makes things simpler, but you can also add another disturbance here that is directly coming to the system dynamics as well. And I need to know that the disturbance is coming from a bounded set. So it is taken from this L infinity functions, which is bounded with this term, let's say D bar, obviously. But the definition here is, first, I'm going to give you the robust safety definition, where the only change is highlighted with the red. Basically, now we are calling the system robustly safe if the original safety condition is satisfied for all D that can be realized from this set. And for this problem, there are a lot of works in the literature And this was taken from maybe 3 or 4 years ago. I believe the last 3 or 4 years, there should be maybe 10, 15, 20 more papers. Most of these papers focuses on how to eliminate unnecessary conservativeness by maybe learning some part of uncertainty, and can we integrate that uncertainty back? So there are some estimators, observers, some learning methods, and etc. These are really cool, but again, I'd like to talk about the input to state safety, where what is different from the robust safety is basically we are looking for another lower bound on the right-hand side, where instead of this absolute zero, can we just relax this, find a certain representation with respect to that is going to change with respect to the how large the disturbance is. So when we check the literature, you're gonna see there's mainly two types of input to state safety definition. The first one is basically is more associated with the input to state safety. It has some temporal characteristics on the right-hand side. But there's some restriction. I don't really understand why it is defined that way. Maybe someone here may have a better idea, but I would really appreciate an explanation as well. But I'm going to show you with the class K function, class double K function used on the right-hand side. It is somehow restrictive, so it wants the lower bound to basically increase in time. Whereas on the other hand, there's this type B type of definition. It's easier to use this definition to construct controllers. It doesn't have any temporal characteristics, so for all the time, we have the same constant degradation. We will use this type of definition to find some sufficient conditions that actually implies this definition. And I said this is somehow includes type A, but you need to take this with a grain of salt because the problems that they are constructed on are slightly different. So in the type A, the safe set is an open set, and the type B safe set is a closed set. So from there are some differences. But if you actually project the type of definition in type A, type B is somehow more general, and I will show it here right now. So here, the formal definition of type A, we will call the system is input to state safe if you have two functions that will be used to lower bound the system trajectories. The first function is a gamma, it's a KK function. Well, that means basically it has both arguments, and both arguments are going to be class K function. And then there's another just class K function, the sigma, that is going to be there as well. So this type of bound naturally gives, or it shows a characteristic like this because of the class KK property of gamma. Since based on the second argument, as time moves on, you would want a larger and larger gamma. So at some point, it may cross. So this type of temporal characteristic, it may make sense in terms of input to state stability. And as a matter of fact, they actually show input to state stability can be used as a sufficient condition with some other condition to get the definition that they make here. But I find this a little bit restrictive, because what if my controller has a property like this, that it actually converges to this bound? in that case, there's no way of um, representing this. So I find this a little bit restrictive. So this is why we typically use the second notion of input to state safety, where we do not have those temporal characteristic. We just kind of push the zero absolute robust safety to a little bit degradation, and that degradation is going to take characterization based on the sigma function. It's a class K function. So if there's actually no disturbance, this is going to be zero. You're going to have the normal safety. But if it's large, then you will get a larger and larger and larger deviation. So this is the type of input to state safety that I will talk. And we can actually get some sufficient condition that is coming from the control barrier function, basically with a modification given here. If you add this modification to your CBF condition, you will show that you actually can get a sigma, which is given here. It can be shown to be class K. So it is a very practical way of showing that a system is input to states safe, but also you can construct the controller such that the resulting closed loop system has input to state safety. And indeed, as I said, this gives us a very easy to implement type of condition. So I just changed something in the safety filter. And when I redid these experiments, what I realized is, well, yes, you are safe, but you're also very far away from the other car. That means that this part, this new addition, is actually introducing a huge conservativeness to you. So this is not no way acceptable. This is one of the things that I discussed at the beginning of the presentation. There's a huge difference between the theoretical guarantee and the practice. Now, I will introduce another method that is going to kind of bridge this difference. So the idea here is, this is the sufficient condition in the previous case. You can see that doesn't really scale well with the disturbance. And I would like to find a maybe better idea or better modification that is going to accept more characterization, so I can tune it based on how far I am from the safety boundary. For example, if I'm very inside, I'm very far away from the boundary, then I don't really need this much modification anyway. So the idea is, instead of using a constant epsilon, I just want to make it a function of h, because h is a characterization of how safe I am. The whole theory is here. I'd like to go over it, but I'm not going to really spend too much time on it. But the idea is, if you can find a certain epsilon function, it needs to be continuously differentiable, and its derivative has to be basically negative, just like a exponential function, basically. So instead of this constant epsilon, if you use this epsilon on the right-hand side, then you can still get type B type of ISSF. And you can also get whatever this sigma function that is going to, in the end, will give you the degradation. But in this time, you cannot explicitly take that. It is going to be the implicit, or the solution of this implicit function. So it shows itself here and here. You need to basically solve this question, which is not a big deal. And you can actually use the implicit function theorem to show that this indeed has a solution and it's unique. And it is also a class K function. So everything fits in the theory. And as a matter of fact, you can also show that this tunable variant is better than not tunable variant. It's closer to the real degradation. We can show it in an example. You can just take this 1D example of nonlinear dynamics here, and I'm adding a disturbance with a bounded disturbance can take maximum value of 1. The set is going to be just the positive values. So I try to be on the positive values. If I don't have any disturbance, then I can basically use the barrier functions to show that it is actually safe, because this holds. And in any initial condition you can start, you're going to see that you will not actually leave the set S. However, if you introduce a disturbance, for example, a sine signal, then you're going to see that there is actually some instances that you leave the intended original safe set. And our goal is to find out how much this degradation is going to be. So if we use the not tunable version, we can make the calculations and find the residual term here. And based on this residual term, we can calculate a sigma function, how much it expands. This is what it tells me, the red one. It does capture, it is true, but as you can see, there's a huge difference between what is going on in practice and how much you get from the formal theory. On the other hand, with the improvement we introduced with the tunability, you can actually have the flexibility to get a residual factor with a function of x. So it does ensure the input to state safety, and you can solve that equation implicitly to calculate this bound. And as you can see, this bound is way closer to the practical setup. So this is a way to, again, bridge the theory in practice. Now I go back to this chart because I believe the input to state safety, and especially this tunable implementation, it aligns very, very well with this landscape, where with the theoretical foundations, we can get a formulation for a safety critical control. We can compute and implement this to a system, and using the data in the experimental setup, we can get some estimation, and we can implement some learning methods basically to understand what this disturbance is going to be. And this can be integrated in this framework to update these parameters of these quadratic programming, so that in an episodic way, iteratively, you're actually getting better, and better. So I believe the input to state safety plays a huge role in this. And at the end of the day, this is what we did with the truck as well. As you can see, with the robust safety filter, with the tunability now, we do have a good performance, we have safety, and indeed we do have safety in the data as well. So at the end, this is the experimental setup where we showed that it actually works. With this, I'd like to finish on two things. First, the outlook. So far, I talked about basically the fundamentals of input to state safety. But recently, you can also see there's kind of a push in the input to state safety in merging it with the complex systems. So basically using the input to state safety to understand, to analyze behavior of complex nonlinear systems when it comes to safety. The first line of work, I would say, this is switch and hybrid and event triggered systems. I saw some paper, and as you can see, these are pretty new. The other one is, which is I think more promising, and I'd like to actually spend more time on this as well. And I think there's also a counterpart in the input to state stability for that as well. So we can maybe find ways to give us input to state safety in a better scalable way. So if you have large network and connected systems, by basically analyzing some sub part of that whole system, maybe you can tell something about how the whole network behaves. So there are some works on that as well. This is the main takeaway. I think I pretty much explained what I wanted to talk about. The control barrier functions, I think they are very promising in guaranteeing safety. We can use safety filters using the CBFs, but disturbances are something that we have to deal with because they do have the degradation. And how much this degradation can be characterized by input to state safety. And I think this whole idea kind of completes an iterative safety critical control design cycle again. And with that note, I'd like to finish and thank you for listening to my talk.